So hello guys, today we'll be discussing another problem, and we'll be discussing the problem of the day of yesterday's problem. So before moving on, I would like to remind you that today we'll be having a contest, that is code to contribute, from 7:30 to 9 p.m. It will be a 90 minutes contest. So guys, I hope that you must have registered, so please do participate in that. And now let's moving further. We'll be discussing the problem statement or the question, right? The name of the question is generate parenthesis. So as you can see here that it is a good question, and the topics include are also good, that is backtracking, recursion, and it is asked in, like you can see from here, that a top tech giants company, right? So we'll be solving this problem. So let me open the problem statement for you. So yeah, basically the problem statement says that we are given an integer n, representing the number of pairs of parentheses, and the task is to generate all the possible combinations, or generate all combinations of well formed means balanced parentheses. So basically we are given an integer, right, which will be representing or denoting the number of pairs of parentheses that we have to use to generate all the possible combinations we can generate with those pairs of parentheses, right? So suppose in case of n equal to 3, so if I move to the whiteboard, suppose, so if we have n equal to 3, so that means we'll be having three pairs of this parenthesis, so it will be first, second and third. And now we have to find all the combinations using all these pairs to generate all the possible parentheses we can have, right? So yeah, so from here we can see that these are all the possible pairs of parentheses we can have, right? So we have to generate all these parentheses. So let us now see, and let us now look at the constraint, or the constraint is 12, right? So I'll tell you why the constraint is only 12 in this case, right? So let us now move to the discussion section, where we will be discussing about how we will approach this problem statement, right? So as now the problem says that we have to generate all parentheses, right? So from this term generate all, right, so we can assume that we'll be working in a brute force manner, right? Because there is no other way than other than using brute force approach to generate all the possible combinations, right? So in the previous lectures and the live sessions also, I told you about the recursion function, or the recursion functions body, right? So if this is my recursion function, right, it is having some parameters, it is having some return type. So sorry, and it is having some return type, right? So what is the first step? The first step is like the base condition, with the help of which our recursion will stop, and it will prevent the recursion function going to the infinite loop. Second is the statements, right? So basically how do we write or find this recursive function, right? How do we find this recursive function? We normally look look out to the task we were given, right? We will look out to this factor in bit of seconds. And the third one is the normal return type, right? So that means that what we have to return from this, what do we want to return from this recursion function, right? So this is the recursion body. Why I'm telling you this? Because we'll be using this recursion, or maybe I can say backtracking, because backtracking is also recursion, right? So it is a case of recursion, right? So I'll tell you this a bit, right? I'll tell you this, no issues. So as I told that we have some how do we define this recursive function? We just look out the task that we are given, right? So in this we have to generate all the possible parentheses, right? So if I say that at a particular state, because for learning recursion we draw the recursion tree, right, to understand recursion better and how the recursion function will work. So we draw a recursion tree. So suppose if I draw a recursion tree like something like that, right? So how it will be working? Suppose if I'm so as we all know that these are called the states, right? States of recursion, all these nodes are called states. So if I'm currently at a particular state, then what choices I am having? I'm having two choices, right? Whether to and suppose, okay, I am storing my final answer in the string, right? Suppose let it be string answer, right? Initially it is empty. So at the first state, right, when suppose for n equal to 1, I have two choices, right? That is either whether to include this one or this one, right? I have a choice. So on the basis of choice, we draw a recursion tree. How? Suppose if I'm state at n equal to 1, then I have two choices, right? Initially my string is empty. So if I draw it more clearly on a fresher page, so how we can look at that, right? So the best way to learn recursion or backtracking, or to understand how we'll implement backtracking or recursion, is to draw the recursion tree, right? So yeah, so as I draw the recursion tree, right, so if this is, I'm currently at this state, right? So initially my value of uh, right, so initially I have used 0 open brackets and 0 closing brackets, right? Because we are having only these two types of brackets, right? So yeah, so okay, let's forget about this open and these terms like open and close bracket. We only discuss about our approach, what we are trying to do. So basically we are at each step we are having two choices, right? That is to include this one in the final answer or this one, right? So initially my string is empty, right? Initially, let me delete it. So initially my string is empty, right? I'm not having anything. So it is the first, or the initial state, right? Or we can say the root of that tree, recursive tree. So in the first state, I have two choices, whether to sorry, whether to include this one, and if I include this one, what will my string will look like? My string will look like this, right? Or to include this one, right? So if I include this closing bracket, my string will look like this, and if I include the open bracket, my string will look like this, right? Similarly, if I follow this state, right, if I continue, because we will continue this in the depth wise manner, because we all know that recursion works in the what depth DFS manner, right? That is depth first search. So once we are started with this, we will be doing computations and going in deep with this branch only, till we reach the leaf node or till we reach the base condition, right? So once I have entered this, I'll again go to this, right? In this state also I'll be having two choices, right? Whether to include this open bracket or close bracket. If I include the open bracket, my string will now look like this, and if I insert the close bracket, my string will look like this, right? So this is how our recursion tree will be drawing, and this is what basically we'll be doing, right? So this was the basic general idea what we'll do, right? So yeah, so now how can we do that? So this is, in this manner we'll be generating all the possible parentheses. I hope you are aware of the quotient, in that we have to generate all the possible subsets, right? So in that also we have two choices, right? To either to include that element in the subset or not, if we do it recursively, right? So let us now see, we'll discuss how backtracking is used here, but first of all let us now have the overview of the complete approach what we'll be doing. So what we do here, at each state we have a choice whether to include the open bracket or the close bracket in that string, right? And yeah, now after that, what we'll be doing, using this concept, right, that is at each step include open or close, we'll be generating all the possible parentheses, right, we can have. And after generating all the possible parentheses, we'll be looking which one is the balanced one, right? So basically I'm dividing this question in the naive approach, I'm dividing this question into two parts. First part is generating all parentheses, right? And in this all the right ones and all the wrongs one, all the wrong ones will be there. Right means balanced one, right? And the wrong one means unbalanced one. And now in the second step, after all these parentheses are generated, all the combinations of these parentheses are generated, I'll be checking out of all these which one is balanced and which one is not. If any of the generated parentheses pattern is balanced, then I'll put in the final answer, right? Else I will not. So in the second, I'll be checking, right, which one is balanced and included in the final answer, right? So this is the first approach. I hope this approach is clear to you, right? So uh, yeah, so let us now discuss this approach only, right? So because in this approach we'll be discussing about backtracking, right? So the main concept or the main idea here is backtracking. So how we'll be using backtracking? So again, to understand this, I'll be taking an example and I'll be drawing the recursion tree to help you make it understand faster and more efficiently, right? So that you don't have to mug it up, you learn the actual concept, right? Because most of the students I have seen, they don't feel the recursion by their heart. They just mug the they just mug up the code, because we know that recursion code is very small, so they mug it up and they don't realize or feel the main essence of that recursion function, right? So yeah, so if I call my recursive function as solve, right? So what we'll be doing, so yeah, this is my recursive function, right? So what we'll do, uh, yeah, so as I told that, okay, let us delete it. I was talking about recursive function, right? The recursive tree. So how backtracking will work? Suppose if n equal to 2, I'll explain it with an example, right? Suppose n equal to 2, that means we have two pairs, right? This, right? So we have to generate all the possible answers, right? So initially my string will be empty, right? So in this first state I'll be including whether the open bracket or the close bracket. If I include the open bracket, this is how my string will look like, right? And if I, right, so yeah, so as we know that the recursive, if I draw the recursion tree, right, if I draw the recursion tree like this, just to remind you again in case you forgot, so the recursive function always work in this manner, right? It will always cover the left branch or the left subtree, then it will go to the right, right? So this is how it is working. So I hope you understood, right? So that's why I'm saying here that uh, once we include the open bracket, we will be again going in this and again include the open bracket, right? Again, if I include the open bracket, this will look like this. Now the base condition in now how will I know that I have to stop? I will know that when I will have two counters, right? One is for open bracket and another one for the close one, right? So these will be storing the counts of the brackets, open or close bracket, we have used till now, right? So in this case I have exhausted all my open brackets, so I'll return right from this point only. So okay, so once I have reached the base condition or the last, I'll include this in my final answer, right? Like I will include it in the possible answer, right? So I will put it in an temporary, let us say temporary vector of strings, right? So I don't know whether it will be my answer or not. I'll be checking it, because what I am doing, I'm just generating all the possible parenthesis combination and I'll be checking at the end, right? So the uh, first one generated was this one, right? Now what how does backtracking performs, how does it work? So once you reach the base condition, right, so it will the stack will unwind itself, because in recursion we have stacks, right? So once this recursive function or the recursive call is done with its current state, this state, it will again pass its answer or the return statement. In this it will be void, that it will not be turning anything. It will return to its parent state, right? Or it will return to its parent function call. So for this state, its parent function call was this, right? I mean, for this state, its parent function call was this one, right? So it will return after performing all the computations in its individual state, in its own state, it will return to its parent state. Now in the parent state, what was the string, right? Because in this state, in this state, the final string was this one, right? Now in the parent state, what was the string? The string was only this one, right? So this is how we automatically backtracked, right? So now in this state, in this state, in this state, we have string this, right? So now we have we have the second choice as including the close bracket. So how we will do that? This one, right? So I'll also include this one in the answer, right? So this is my temp array, complete temp array, right? I'll draw this like something like this. So this is my another string or the parenthesis combination generated. So I'll check all these at the last, right? Now currently now I'm just adding or generating all the possible parentheses, right? So yeah, so after this one, after this state, I know that I have still one open and one close left, right? So I can still add one open and close to this one, right? So what I'll do, I will again add one parenthesis to this, and it will again go on, right? So now I have reached this state, right? So now I know that yeah, so now I know that I cannot add anything open bracket, right? So what I'll do, so actually here also, before reaching this state, it will again now for this state, right? We had two choices at this state, right? Whether to include the open bracket. So now here we don't have any open bracket to be added up, right? So I will, this will not be called up, right? Now I will go to this one and I will check. Yeah, I have do I have an option of adding close bracket? Yeah, I have. So I will add an close bracket here. So my string will look like this. Now again I'll not having any what I can say, I will not having any chances of adding the open bracket because we have exhausted all the open brackets. So I'll only have the facility of adding the close bracket again, right? So because we are again still left with one close bracket, so in this manner, right? So yeah, now we are not left with anything else, right? So the base condition will be so what will be the base condition? The base condition will be when our open and close bracket are exhausted completely, right? Then we will be adding it to the final answer, right? So it will be my base condition. I'll be writing down each and every step. Once for now only we will be discussing how we are doing backtracking, right? So this is how the complete this is how the complete what I say, the complete recursive tree will be drawn, right? So I hope you understood it. If not, then we can again, like we can do some again or more computations, right? So after this complete is done, we'll backtrack, right? From here we'll be backtracking to this, right? So it will return this, right? And in this state the string was this, right? And again from here I'll be backtracking to here, then to here, then here, right? So this is how it will go on. How it is backtracking? So actually you must have learned that in backtracking, once we insert, then we pop back all the operations we performed so as to backtrack, right? So that is the one approach. The another approach, which is very easier one, and it takes lesser number of what I can say, lesser number of operations, right? And it is much faster, is that don't add something, right? And so what we do, one concept here I would like to introduce to you is that at each and every step, right? At each and every step you pass some, for each and every step, what does it mean? For each and every step you pass some recursive function, right? So for this state you have a recursive function, let us name it solve, right? You have a recursive function named solve, and it has some parameters, or we can say instead of parameters we can say that it has some its own attributes, right? In its own element. For in this case it will have what, it will have a string, right? That is temp string, which we were using, that is this one, right? For each state it is having, each state will have a temp string storing the current parenthesis generated till that state, and will have an open count and the close count, right? So all these parameters or the elements will be available for each and every state, right? So what the concept is, for each and every step in the recursive tree or the recursive call, this all these parameters are have the value only for that state only, right? So if suppose at this state we had some values of string, suppose at this state we had some value of strings, right? Suppose the value of temp was what say, let us this one, right? And at this state the value of temp was, let me say like this, right? So and value of open for itself, let us suppose say 2, and close For instance, let us say it was 3, right? So these values are only for this state only. If we change our state, these values will be changed, and the changed values will be for that state only. How? So if I have done all the computations for this state, once we backtrack, or once we call once this state call its parent recursive function, so all these states will be vanished, and this state and all these variables will be established to the elements of this state only, right? All these will be vanished. It will not be kept as it is, right? So as you can see that in case we applied ampersand, all these changes would have been remained as it is, right? But we are not using ampersand. The main concept of not using ampersand is that we don't want the changes to be reflected in each and every state. We want, what do we want? We want that each state have its own set of values and parameters, right? Because for each state, the open and close or the temporary string are will be having its own and different values, right? You will understand it further better when we'll learn, or will be learning or drawing in more deeper manner, right? So this is why, this is how we'll be backtracking, right? So now once we have generated all the parentheses, we'll be checking one by one whether which one of will satisfy and which one of will not be a balanced parenthesis. So this is the one approach. But can you see that we have to generate in this manner, we will have to generate all the possible parentheses. But can we do it something better? Yeah, we can do that. We have to do some observations, right? So I hope that first of all, you before moving further, you would have understood the main concept, how we are backtracking and why we are not using ampersand. Because if if I would have used ampersand, right? If I would have used ampersand, for example, for this string, I would have used ampersand. So again, if I draw the recursive tree for this one, suppose at this state, at this state, my value of temp was, for example, let us say this, right? And if I made some changes to this, if I made or added one here, right? So when this state would have called its parent state, then this same temp would have been passed to this one, right? Because we had used ampersand, and the changes made to this temp will be independent of the state in which we have made the changes. It will be reflected in all the changes made at each and every state will be reflected in all the states, right? But we don't want that. How? Because why we don't want that? Because basically once we backtrack, right? So what do we how we are using the concept of backtracking here? Suppose let us move to the part where we were solving, right? So here we were solving here, right? So you can see from here that once we reached here, right? Suppose we did all these computations and we reached here. Now I wanted, so for this state the value of temporary string was this one, right? For this state. Now once we backtracked here, we again fetched this value so that we can add the new strings, right? We can generate a new possible combination. So that's why I hadn't used ampersand. If I would have been using the ampersand, I would have to perform the pop back operation from the string. That is, uh, before this state before this state calls its parent function, I would have to pop back the last added parenthesis, right? But I don't want to mess it up or perform a larger number of computations. That's why I am not using ampersand here, right? So I hope so when I'll be coding down, you will realize that how easier it becomes when you don't do backtracking in the manner when we push and then pop, right? So you will analyze and see and feel that how easy it becomes when we don't use such type of operations, right? So I hope you now understood that how we are using backtracking and why we are not using ampersand. I'll repeat it for you again, because if I wanted to generate a new parenthesis, right? So if I'm at this state, so my current generated parenthesis was this, right? Now I wanted to generate a new one. So after this state has performed all its computation, it will call its parent recursive function, right? This one. And at this state we know that we only had the generated parenthesis was this, right? The combination was this, so I can add now one to this, right? So you can see here. So yeah, so this was the approach. So the time complexity of this approach is right 2 raised to the power n. Why? Because at each and every step we are having two choices, right? We have two options, either to include the open bracket or the closed bracket. So this is the approach, right? And yeah, so how we can improve this, right? Because you can see that we are generating all the possible parenthesis combination, and those all generated parenthesis combination will also include the useless, that is the unbalanced one, but we don't want them. So how we can uh, improve our code, right, to do the, although the time complexity will be 2 raised to the power n only, right, but the number of computations will be reduced, and it will help you in the larger values of n, right? So what observation we are looking for? The observation, let us now take an example, right, to understand this better. For n equal to 2, right? So let us generate all the possible parentheses we can have, right? So the balanced parenthesis. So this is one, this is the another one, right? Do you think any other possible parenthesis is available for that? No. Only these two are the possible parentheses. Now you observe one thing, right? Let us start from one by one step, right? Suppose if the step 1, right, I included this parenthesis, right, this open bracket. Now do you think that we had two options, right, to either to include the open one or the closed one. How we will decide which one to include? So you can see there, okay, so from one bracket you will not be able to observe it. Let us now, for instance, say we just chose the closed one, right? Now do you think it is, now in the next state we again have two choices, whether to include the open one or the closed one. Now do you feel that it is logical to add a closed one here? No, right? Because, why no? Because we had only one open bracket and it was balanced or nullified by this closed bracket. So there is no logic of adding a closed bracket, because for this closed bracket we will be using for what I can say, for this closed bracket that I'll be using will not be having any open bracket for it, right? For this one there will be no open bracket for to nullify this closed bracket, right? So there is no logic for including that, so we can remove such combinations, right? So how we decided that, how will not, because we know it manually, right? But how do the computer knows it? So what we'll be doing, we'll be wisely doing an operation, right? We'll be looking an observation. The observation is that you will observe that when the when the count of the closed brackets is less than the open bracket, then we will add it, right? Because for example, if I had this open bracket and closed bracket, now the count of both open and closed brackets are equal, and the count of open bracket is 1 and the count of closed bracket is also 1. So now we will not add any closed bracket, right? But in case if the count of, suppose if I add a open bracket here, now the count of open bracket is greater than count of closed bracket, right? So because the count of open bracket is now 2 and the close is 1, so now the count is less, so that means we still have any we still have an open bracket that has to be nullified, right? So that's why we have a facility or option to add the closed bracket, so then only we can add the closed bracket, right? So that's why we'll add closed bracket. Now this was all about the closed bracket. Now when we'll be adding the open bracket, so there is no basically condition for adding the open bracket, right, as in the closed bracket. Why? Because we can add closed brackets anywhere we want, but up till when? Up till the condition when the total number of open brackets available to us are not exhausted, right? So how, suppose I added this open bracket, again I can add this open bracket for n equal to 2, right? But now the open brackets are all consumed up, so we cannot use that, right? So this is how we'll be some doing smart observations and reducing generating all the possible combinations we generated, right? So yeah, so let us now look how it will be working. Let us now move to the pseudocode part of it. So what we'll be doing, will now let us name our recursive function as solve, right? Let us now name our recursive function as solve, and the return type will be void because we are not returning anything, right? Void. And what we'll be having, we'll be having string, right? String temp. That means temp denotes the currently generated parenthesis combination for that particular state, the count of the open bracket and the count of the closed bracket, right? So now what will be the base condition for it, right? Because for for every recursive function, it is universal that we have to have a base condition, right? So what will be the base condition? So in this we can see the base condition, or when we will stop when the count of the open bracket and close bracket will be equal, right? So now how we are so sure that when the count of the open bracket and close bracket will be equal, we will be getting a balanced one? How? Because the statement I'm saying that uh, will be stopping when all the count of the open and close bracket will be equal. Let us try to do a contradiction to that, right? So suppose if this is my generated parenthesis, in this also the count of open and close brackets are equal, right? But it is not a balanced one. So how we are ensuring that when the count of the open and close brackets are equal, when the count of open and close brackets are equal, then we will be surely getting a uh, what? Then we'll be surely getting a balanced parenthesis. How? This is because we, while inserting the bracket, we are ensuring that we'll only add close bracket when the count of close is less than open, and right, and we can add open bracket as and when we want until the point the count of the open bracket is less than n, right? So since we are ensuring before adding the close bracket, we are ensured that our final answer will be a balanced parenthesis when the open and close brackets have count equals, right? So because of this condition, the smart condition we are using to insert the close bracket, we are ensured and guaranteed that when the count of open and close brackets are equal, we will be getting the what? A balanced parenthesis. Let us take an example for that, right? I'll prove it to you. Now, this is my open bracket, right? Now, if I add, now I see that my count of close is less than open one, so I will add this. Now you can see that both of the counts are equal and it is a balanced one. This was the first case. Let us look at the second case. Right? Let us look at the second case. I added this one, and I added again this one. I added this one, right? And so now here I can see that my count is less than my count of close is less than open one, right? So and it is also not balanced one, right? Once I add the close one, the count of open and close become equal. Now it becomes balanced, right? So that's how you can feel that, right? So it is the proof here. So yeah, so this is my base condition. The base condition will be when my open and closed count will be equal. I will know that the current string, right, or the generated parenthesis is my answer. So what I'll store this into a, what say, an vector or array of strings. So I will push that answer. That is, suppose my final answer is answer, right? So I'll push that in my this temporary, in that final answer, and I'll be returning, right? Why return? Because this is our base condition, and we, after the base condition we normally return, right? After the every base condition we return back to the previous parent function, right? So now we had two choices, right? And those choices were based on the if some conditions. The first condition is that, so yeah, the first condition is that uh, if the count of close is less than open, then only we will be adding the what, the close bracket to the current temporary or the generated parenthesis, right? So for that we'll be calling our solve function, and in the temporary string we'll be adding the closed bracket, right? The closed bracket will be adding this will add the close bracket to that, right, to that current string, and open count will remain as it is, but the close count will be incremented by 1, right? Now we can add the open one, right? because open, but the addition of the open bracket is independent of the count. It is only dependent on the factor that the count should be less than only n, right? It is unlike the close one. The close one is dependent on the open one, right? But the open is not dependent on close one. It is only dependent on the total count, that is n. So if my open one is less than the count n, then I'll call solve function, that is I'll add this open bracket, right? Increment the count of open by 1, and the close count will not be increased in this case, right? So how it will be working? So suppose let us do iterations and like run this code, right? So for example, for n equal to, let us say for n equal to 2 only, initially my open and close will have count 0, right? And my string will be also empty. So now I'll see my in the first recursive call from the main function, I will see that my close is 0 and open is also 0. So this condition is not met. So this condition will be met, right? So my string will become this one, right? My string will become this one. Count of open will become 1 and count of close will become 0. Now, once it calls the recursive function, we reach to the next state, and in the next state, from there we reach to the next state. In the next state we'll see, yeah, the count of close is now less than open, right? So we'll add this one. So now in the next state our answer will become something like look like this, and we'll again increment the count of close by 1. So open will remain 1 and close will remain 1, right? So once it calls here, it will see that, yeah, open equal to close, then we'll return back normally, right? So once it returned from here, so once it returned from here, uh, what we'll do, we'll then again after this, we have not used the else condition here, right? So that's why it will also run with this also, right? So in the similar fashion all the computations will be done. Let us now move to the coding part, right? So to see, so you can also see the time complexity is 2 raised to the power n here only, right? So time complexity is 2 raised to the power n only. We just use this smartly to reduce the number of computations only, right? So I hope this is clear to you. So now we'll be moving on to the coding part. Right, so just to summarize it, we are discussing about the problem of the day, and the problem was that we had to find all the balanced parentheses, right? And because we knew that to generate all the possible parentheses there is only one way, that is using the brute force manner. So for the brute force we are using recursion here. So solving it recursively, we generated we took all and each and every possible, we generated each and every possible combination, right? So that's why, so that's how we looked it. Okay, I have made a mistake here, can you identify it? So what condition I have used here, right? The base condition I used here is that when open is equal to close. But do you think that once we did this, uh, it will work? It will. Do you think that? Do you feel that this condition will stop me from generating the other or the remaining of the parenthesis? I made this mistake, uh, like purposefully, so that you understand that how to analyze the base condition, right? Because many of the people will be thinking that, yeah, this can be the possible base condition, but no. For example, if open equal to close, in this case also, right, for open equal to close, we will be returning, but once we return we will not be able to generate this parenthesis, right? Will not be able to generate this one, this part, because every time we generate all this we'll be returning back, right? We will be returning back. So do you feel that uh, what demerit or what drawback will it come with this base condition? I hope you understood it, right? So I made it mistake. Trust me, I made this mistake purposefully, just to make you understand that yeah, many people will think that I too for at the first thought that this can be a base condition, but when I analyzed it, I saw yeah that this will provide me an error, right? So what will be the correct base condition? The correct base condition will be, so you analyzed, right? You understood that so the correct base condition, what it will be. Let me first cancel it out, right? This is not the answer, so that nobody gets confused. Wrong base condition, right? This is wrong, right? So I hope that in the future you will not be making this kind of mistake, because we only learn from our mistakes. So what will be the correct base condition? So now you can feel that this whole uh, so on what factor we can determine that yeah we have got a final answer. Only when, once you observe, you can feel that only when our the close brackets have reached its final count, then we can ensure that yeah we have reached our final answer. How? Let us take an example again. If this one, right, and yeah this one, so do you think that I'm still over with my all the brackets? No, I do have left for n equal to 2, I do have left an open close bracket, right? So this one the close bracket. So once my close brackets have reached the count of close brackets have reached the count equal to n, then I can say that it is my base condition, and we have to return it from there onwards, right? So this will the base condition, the correct base condition will be, the correct base condition will be when my count of close will be equal n, then I can be ensured that it will be a balanced string, and I have exhausted all my available options of adding it, right? So because we are always adding the close bracket at the last, because we have to why last? Because we have to nullify the open bracket, right? Then only it will be becoming a balanced, then only it will be becoming a balanced generated parenthesis, right? So that's why we are always adding up the close bracket when the count of the close bracket is less than the open one, and by this logic we'll be adding a close bracket or get exhausted by our close bracket at the end always, right? So this is how this is what about the base condition, right? So this is our base condition, and once it is reached we'll be adding it, that particular generated parenthesis, in our answer, and we'll be returning back, right? So yeah, so let us now move to the coding part, guys. So this is a practice portal, right? You must be aware of that after all the problem of the day, right? So yeah, so let us now code it down, right? So now let us look at the return type, what we have to return. So we have to return all the parentheses in the vector of string, right? So I'll be calling a helper function, right? So for that what will I do? First of all, to store my all the answer, I'll be declaring a vector of string. Let us name it answer, right? And a variable open denoting the count of the open brackets and count of the close bracket. Initially all of them will be 0, and I will be having a temporary string which will be initially empty. And now I will be calling my recursive function solve, which will help in finding all the possible parenthesis combination. So what all thing I will be passing it to it that is the answer vector, in which I'll be storing my answer once the base condition is reached, as we saw. And I'll be passing my temporary string, right, and my open count and my close count. That's all. And once this function will be recursive function will complete each and every of its state, um, all our possible generated parentheses will be stored in that final answer. Then we will be normally returning this final answer here. Okay, so let us now write our main function. The return type will be void one because we are not returning anything from it. We are just normally generating all the parentheses and storing it in the final answer. So these are my input parameters. So you should note guys here that here for storing the answer I am using ampersand because I want to reflect the changes in this one in the function in which through which I call this recursive function, right? That's why I'm using ampersand. It has no relation with the backtracking, right? I'm using ampersand only for the fact that I want to reflect the changes and store the answers, right, for each and every state in this one. That's why I'm using ampersand. It has no relation with backtracking and all. Just to clear you, right? I'm having a string temp open and int close one. Let us now write our function. So first one is the base condition. So what will be our base condition? If my the base condition was if close was equal the total count, right? Then I have to return or add into the final answer, right? And then return. If this base condition is not met, I have two options, either to add the close bracket and the open bracket. So what was the condition for adding the close bracket? That is, if my count of close is less than open, then I can add the then only I can add. I'm repeating the sentence. Then only I can add, right? Uh, so I'll call my next recursive function for that. So as discussed, then will be if I can add the close bracket, then I'll append my temporary string, right? And I'll increment the count of close by 1, right? If so, one thing you should note that here at a state I can add the close and the open one also. That's why I'm not using else condition here, right? Because uh, uh, suppose at a particular state I am having two options to add a open and a close one, right? For example, let us take this one, right? So if I've added this close bracket here, then I can also add the open one, right? Because there is no condition on open bracket. The only condition is that we can we can only that the only condition is that it is we can add the open bracket once only when its count is less than the total open brackets available to us, right? So yeah, so if open is less than n, then we will add the open bracket and increment the count of open by 1. And this is all about the recursive function, right? So one thing we are missing here, that the size n is not global, so we have to pass it in each and every recursive call here also. So I think that this is all, right? Let us review our code again. Void string ampersand answer temp open close n close equal to n. Yeah, correct. Yeah, let us try to run it. Hmm. Refresh it again. There are sometimes some backend type of errors, right? They happen. So for that we just have to, but anytime you face that such kind of error, you just refresh it, log in again, because that session is ended if you are not if you're not active in that session for too much time, right? For some time, so that session is closed. So for that you have to again refresh it, right, and log in again. So now it will work, right? You can see it here. So yeah, small n. So as you can see, it is getting accepted. So that's all about, guys, backtracking, recursion, and the so this is a this is a very basic and a beginner problem to understand the backtracking, right? One more problem you can solve like this is that generating all the possible parent subsets of a string, right? Generate all the possible subsets. So the same concept will be used here. So you can do that question for your practice, guys. So just to remind you guys again, the contest, that is code to contribute, will be starting from 7:30 to 9 today. So do participate in large amounts, and all the best, guys, for that contest. Happy coding. Bye bye.